Right, ladies and gentlemen, let's continue with Chapter 8. We have done the introduction. We've looked at how to calculate the average mean temperature in a tube or an internal geometry. We have looked at the complications of the entrance region, specifically the development of the velocity profile and the temperature profile. And then in paragraph 8.4, we did a general thermal analysis of two possibilities of a constant heat flux problem and a constant wall temperature problem. And I've showed to you how important it is that in the cases where we do not have a constant wall temperature, to use rather for the delta T, the log mean temperature difference. So we've introduced the concept of the log mean temperature difference, the derivation of it, and what it means. Then we've looked at laminar flow, for the cases of laminar flow. And the first thing that people think of when they think of laminar flow is the Reynolds number is 4.36 for constant heat flux, and for constant wall temperature is 3.66. That is correct. However, the however is, it is for the fully developed flow part. It is not for the developing flow part. And we need some additional equations or information if we work in those regions. For the case where we have a constant wall temperature, there's an equation in your textbook, which is the Edwards equation that you can use. However, for the constant heat flux case, there's not an easy equation that you can use. So therefore, there's nothing in your textbook in that regard. But there are equations available. And then the last part is turbulent flow in tubes. So before we go over to turbulent flow in tubes, I want to do an example of flow of oil in a pipeline. And this flow of oil is oil that flows underneath an icy lake. So here's the lake, and there's a pipeline, and oil is being pumped through it. The inlet temperature of the oil is 20 degrees Celsius, and the velocity of the oil is 2 meters per second, the average velocity when it enters this icy lake. So this is the icy lake. We've got ice water there, and in the water there's also ice. Okay, so it means that if we look at this case, that the wall temperature is going to remain constant at approximately 0 degrees Celsius. Do you agree? Okay, so if we look at this, then Ts is equal to 0, Ts is equal to 0, therefore it is a constant wall temperature problem. Constant wall temperature problem. Now, what is also given is that the tube diameter is 300 millimeters. Okay, and the length of the tube is 200 meters. 200 meter tube. And we are asked to determine the outlet temperature of the oil, the heat transfer rate that will occur, as well as the pump power. The pump power required to pump this oil underneath the icy lake. Okay. Now, before we start these problems, we always need properties. Okay, properties like Cp, viscosities, etc., etc. So the question is always, at what temperature do we get it? So I've already told you, go and look in table A13 in your textbook. At the bottom of the page, you will see, for example, the properties of oil. Can you see it? Okay. And, however, it is given at different temperatures. So the question is now, at what temperature must you select it? And as a guideline, we've given you the information that typically use the bulk temperature. And the bulk temperature is equal to the inlet temperature plus the outlet temperature divided by 2. Now the inlet temperature is 20, but in this case we do not have the outlet temperature. Okay, so what do? You take an educated guess. You take an educated guess. What would you choose? All of you? Some of you? Okay. 8? 10? Or 4? Okay. So different values. And obviously the moment you do that, you will see you will have to go and do interpolation in the table, you see? Because in this specific case, the properties actually varies quite a lot for many of the variables between the different temperatures. Do you see? Okay. Now I'm going to be a little bit crazy. So what I'm going to do is, I'm going to select an outlet temperature of -20. Now that would obviously be a ridiculous guess, isn't it? Because if the inlet temperature is 20 and the wall temperature is 0, then the outlet temperature is going to be somewhere in between the two, isn't it? So normally you shouldn't do that. Okay. But if I do that, then I'm going to end up with a bulk temperature of 0. Why did I do that? Well, because 0 is the first value in the table. So I can use the values at 0 degrees Celsius. Okay. So we will later on see if that was such a good assumption. So at 0 degrees Celsius, you'll see the density of the oil is 899 kilograms per cubic meters. The K value is equal to 0.1469 watts per meter Kelvin. The kinematic viscosity is 4.242 multiplied by 10 to the -3 square meters per second. And I think the normal velocity value is also given there, I'm not sure, doesn't matter. The CP value is equal to 1797 joules per kilogram Kelvin, and the Prandtl number is equal to 46.636. Okay. I'm just going to give you the values again. Density 899, the K value 0.1469, the kinematic viscosity 4.242 multiplied by 10 to the -3, the CP value 1797, and the Prandtl 46.636.
Is that not 46,000?
I'm going to get to it just now. Okay. Right, so let's start by calculating the Reynolds number. Why do we need the Reynolds number? So that we can know if the flow is going to be laminar or turbulent. That really helps us in getting the heat transfer coefficients. So the Reynolds number normally is equal to rho Vd divided by the normal viscosity is equal to the velocity multiplied by the diameter divided by the kinematic viscosity. And in this case, I've got the kinematic viscosity, so I can write it like that. The velocity is 2 meters per second. The diameter of the tube is 300 millimeters, so 0.3, divided by the kinematic viscosity, which is equal to 4.242 multiplied by 10 to the -3. And that gives us a Reynolds number of 1,414. Okay. For circular tubes, we know transition occurs about between 2,100 to 2,300. So it's far from there, so the flow is going to be laminar. So our first thing when we think of laminar flow, constant wall temperature, Nusselt number is equal to 3.66. Okay, that is what we normally think. Right. Now, how long is it going to take before the flow is fully developed? Because remember, the Nusselt number 3.66 is for the fully developed part. Okay, so let's just check that. So LT is how long it will take to thermally fully develop, and that is equal to 0.05 multiplied by the Reynolds, the Prandtl multiplied by the diameter. 0.05 multiplied by the Reynolds 1414 multiplied by the Prandtl, which is 46.636, divided by the diameter, it's 0.3, and that gives us 98.94 meters. So, the bigger perspective of this is, and I would always like to encourage you to make graphs. Okay. So if you now think of this tube, which is 200 meters in length, okay, here's about 100 meters, halfway, okay, it's going to take 98 meters before the flow is fully developed thermally. So if we were to put in the thermal boundary layer, it's going to take 98 meters. And that is important information because it means that only after 98 meters, 98.94 meters, only from then on would the Reynolds number be equal to 3.66. Why? For a constant world temperature, fully developed flow, then the Reynolds number is 3.66. And what will happen upstream? Upstream, the Reynolds number will be higher because the heat transfer coefficient will be very thin. The thinner the heat transfer coefficient, the thinner the thermal boundary layer, the higher the heat transfer coefficient will be. So we can see that if we need the average Reynolds number, then most probably it is going to be significantly higher than 3.66. We don't know how much higher, but it's going to be higher.
So shouldn't the velocity in the Reynolds number be 2 and not 20?
Oh, sorry, it should be 0.2, sorry. Sorry. No, oh, sorry, yes, okay, thank you. Inlet velocity is 2 meters per second, yes, okay. Okay. Do you understand this principle? So this is why it is always important that you need to think of the entrance region and what effect the entrance region will have. Let's suppose, as an engineer, let's suppose this was just 98 millimeters. 98 millimeters. Where will 98 millimeters be on this scale? It would be there. Okay. So it would mean that the flow almost right through the tube will be fully developed. And therefore, immediately I could then say the Reynolds number is 3.66. Okay? So it's important. Right, now let's calculate this Reynolds number, and we do it with the Edwards equation. And with the previous lecture, we've done the Edwards equation, and the Edwards equation gives you as the Reynolds number is equal to 3.66 plus the developing part, 0.065 multiplied by D divided by L, multiplied by the Reynolds, multiplied by the Prandtl, divided by 1 plus 0.06, multiplied by D divided by L, multiplied by Reynolds, Prandtl, everything to the 2/3, something like that. Okay. And what is important about this Edwards equation is that this equation does not give us the local value at a specific length L. It gives us the average over the total length. So we must rather say this is the Reynolds number over the total length L. Okay. Look in the fine print of your textbook. You have to go and read it very well. Okay. So this is over the total length. And this makes it much easier for us, because what we now can do is we can say, well, this is the average over that total length. So that Reynolds number that we're going to calculate now is going to be the average if we do the integration of all these local values over a length of 200, then we're going to get that value there. Okay. Now I'm not going to put in all the values for us because it's just going to waste some time, but you can do it at home. I think it's very simple. The diameter is 0.3. The length is 200. The Reynolds number is 1414. The Prandtl number is given. So everything, just plug it in and go and do the calculation. Okay. However, always when you do a calculation, look and think. Do not just do the calculation. So let's suppose this value, after you've calculated, it was 2. Can that make sense? No, it can't. Okay, because it's 3.66 plus something. So it must be more than 3.66. So if we're going to do the calculation, then the Nusselt number over the total length is equal to 4.203. So it is not that much higher. It's 4.203. Right, now that we've got the Nusselt number, we can get the heat transfer coefficient. So the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. And this is, of course, the average Nusselt number. So that is going to be the average heat transfer coefficient over the length L. Let's do the calculation. The Nusselt number is, we've calculated it as 4.203. Is equal to the heat transfer coefficient over the total length multiplied by the diameter, which is 0.3, divided by the thermal conductivity of the oil, which is equal to 0.1469, and then it gives us an average heat transfer coefficient over the total length of 2.058 watts per square meter degrees Celsius. Okay, not such a high value, but there's the value. Okay. Now, just in anticipation of a few things that we're going to calculate now, just for convenience, let's just go and calculate the cross-sectional surface area of the tube. So the cross-sectional surface area, cross-sectional area would be that area there, AS. Okay. And that is equal to, oh no, sorry, now I'm making a mess of it. Yeah. Okay, so sorry, let's use, can we rather use a C for that? Okay, C for cross-sectional area. Okay. AC is equal to pi divided by 4 multiplied by the diameter square. Okay. And if we go and calculate it, it is equal to 0.07069 square meters. Okay, sorry, that should obviously also be AC. Okay, AC, cross-sectional area through which the flow occurs, it is pi divided by 4d squared. Okay, AC and AC. Okay, now the surface area. The surface area is the area over which the heat transfer is going to occur. So if that is the tube like that, okay, then it would be this outside surface area on the perimeter right around it. So that surface area is equal to pi multiplied by the diameter multiplied by the length. And that would then be equal to 188.5 square meters. You all know how to calculate that. Okay. Pi multiplied by the diameter, which is 0.3, the length is 200 meters, and there is the heat transfer area. The mass flow rate of the oil is equal to the density multiplied by the cross-sectional area multiplied by the average velocity. Okay. The density is equal to 899. The cross-sectional area, there we've calculated it, is equal to 0.07069 multiplied by the velocity, I hope I've got it right this time, 2 meters per second. And then that gives us a mass flow rate of 125.6 kilograms per second. Okay. Okay, just a few simple calculations, and you're going to see just now why we're going to use them. Right. Something that we've discussed yesterday is the number of transfer units, the NTUs. Okay, you remember? I hope so. So the number of transfer units, sorry, not yesterday, last week. The number of transfer units is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the CP. And this heat transfer coefficient is obviously the average heat transfer coefficient. I hope you remember it was part of the derivation where we've said we are making that assumption. We've got the average heat transfer coefficient. Right, now we've got the heat transfer coefficient is equal to 2.058 multiplied by the surface area, the mass flow rate we've got, and the CP value, there it is. And then it gives us the number of transfer units as equal to 0.001699. Right, very small. What does it mean? It should already give you some red lights. It means that there's almost not going to be any heat transfer. And if there's no heat transfer, it means that the outlet temperature is not really going to change significantly from the inlet temperature. It gives us a warning. Okay, let's go and see if we are correct. So we have derived this equation for a constant wall temperature. Okay, take note, the equation is only valid for constant wall temperature. So the outlet temperature is equal to the wall temperature minus the wall temperature minus the inlet temperature multiplied by e to the minus NTU. Right, and that gives us an outlet temperature of 19.97 degrees Celsius. Okay, thus, if we try to look at this problem now on a scale of there's x and there's 200 meters, okay, then we have the case where our wall temperature, I hope you can all see the blue, there's the wall temperature, the surface temperature which is equal to 0. Can you see the color? Fine. Okay. And the water temperature would enter at 20 degrees. Okay, so that would be 20 degrees. And the outlet temperature is just going to be 19.97. So the water temperature is just going to do something like that. Almost not going to change. Okay, what is our LMTD? What is our LMTD going to be? Okay, remember, the LMTD is something new. Sometimes students find it difficult interpreting the equation and using it, but it's very simple. This temperature difference, okay? This temperature difference is 20 minus 0, okay? That temperature difference minus this temperature difference, 19.97. 19.97 minus 0 divided by the lim of 20 divided by 19.90. And that is equal to 8.4 degrees Celsius. Does that make sense? Does that make sense? No, it doesn't. Why? And that is usually the advantage if you try to think in your brain what happens. You don't just go through the calculations, but you look at something like that. What would you say is the average temperature difference between the two streams? It should be approximately 20, isn't it? So I've made a calculation error here. Okay, it is actually 19.98. And if you get that, then you should smile, because it means you've done the calculation most probably correctly, isn't it? So think when you do the calculations. Do not just go through the motions. Okay, now we can calculate the heat transfer rate. Because the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. Okay, and the heat transfer rate, the heat transfer coefficient is equal to 2.058 multiplied by the surface area is 188.5 multiplied by the LMTD, which is 19.98, and that gives us a heat transfer rate of 7.752 kilowatts. Okay, and then the pump power was also, what symbol that I use? W. Okay, the pump power. Okay, the pump power is equal to the mass flow rate multiplied by delta P multiplied by rho. There are obviously different ways how you can go and write it. Okay. But we need then the pressure drop. So the pressure drop we calculate as delta P is equal to F L divided by D multiplied by rho V average divided by 2. And then you can go and calculate the pump power. I'm not going to do it now because I want to stop for a specific reason. Okay, and that reason is what this gentleman picked up here. Okay, this is a critical mistake. Okay, please take a re-look in your textbook. Normally when I ask something like this in the test and exams, 90% and more of you would make this mistake. Okay. You have to be very careful for dots and commas in tables and in information. So in terms of normally textbooks and information provided by Americans, that would mean 1,000. Okay, it would mean 1,000. So this should be 46,636. Okay. Now let's suppose that was correct. Let's suppose it was correct. You remember I started by saying, by making this crazy assumption. Do you remember? Outlet temperature is equal to 20. Okay. Now, so therefore I've used a bulk of 0. I would go through all the calculations. I would get 19.96. So what am I supposed to do now? What I'm supposed to do now is to do a new bulk temperature calculation. And you can base it on that. So you can now actually base it on this crazy example. So you can use 20 or 0, and you can redo it. Redo all the calculations, and you'll see in most cases it's not going to change that much. In the test and exams, you do not have to do that. Just write for me that you know you should do it, and then it's fine, because you're not going to have the time. Okay, so let's do this problem the right way. Okay, so let's restart and redo it. So, and I'm not going to write out everything. I'm just going to give you the answers of the calculations because you can go and do it at home. So, what I'm going to do now is I'm going to assume a bulk temperature of 20. Okay. Even with that crazy assumptions. Okay. Now, the Prandtl number, new Prandtl number is going to be 10,863. Okay, 10,863. Now, do you remember what we've said in terms of the influence of the Prandtl number? What it does with heat diffusion? Okay, if the Prandtl number, where can I write? Okay, I'm going to do it here. You remember we had a graph like that, and we've looked at the temperature changes between an inlet stream and an outlet stream. Okay, and the results showed that typically something like that. Okay, and that happens if the Prandtl numbers become smaller. Do you remember? Heat diffuses very quickly. This example is a Prandtl number which is very large. Okay. So the heat diffuses very slowly. Okay. So we can expect rather something like that. Okay. So based on that, let's assume a bulk temperature of 20. Prandtl number is now going to be that. And now we redo all the calculations. And just look at how it changes. If you go and calculate the Reynolds number, then the Reynolds number is going to change to 636. Why? Not because of the Prandtl number, but because of most probably the viscosity, which is going to change a lot. Okay, so if you redo it, you will see the viscosity now changes a lot. However, it's still in the laminar flow regime. Okay, but go and calculate LT now. How long will it take before the flow is fully developed? Well, it is going to be 103,600 meters. So 104 kilometers before the flow is fully developed. 104 kilometers. Okay. Again, on scale. Just look at our scale here. There's 200 meters. Okay. If we go and extend this scale to 104 kilometers, and we scale it correctly, then our 200 meters is approximately there now. Okay. Therefore, what does it mean? 104 kilometers, so it is going to do something like that. It means that all the flow is in the developing region. You see that? Everything is developing, nothing is fully developed. Right, if we go and do the Edwards equation now. Again, just let's come back to the Edwards equation. There it is. It gives us the Nusselt number over the total length. Okay, our length again is 200 meters, but our Prandtl numbers are now totally different. Therefore, our average Nusselt number is equal to 33.7, much higher. So now you see a higher Nusselt number, and then you will think, oh my goodness, more heat transfer, isn't it? If you go and calculate the heat transfer coefficient, then the heat transfer coefficient is higher, 16.3 watts per square meter degree Celsius. Right? If we come back to the NTUs, okay. The NTUs is equal to the heat transfer coefficient, the area, the mass flow rate, and the CP. The only thing that changed now is the heat transfer coefficient. It changed from 2, I've taken it out, something like 2 to 16. So it increases by about 8. However, if we do the calculations for the NTUs, it's still extremely low, 0.001699. So again, it tells us there's no heat transfer. Yep.
So I think that's the NTU of the first calculation.
Okay, sorry. So multiplied by about, let me jippo it by about 4, something like that. Okay. So we'll do that. It's going to be approximately that. But fine. No, you're right. Okay, so it's going to increase, but you'll see it's still extremely low. Right, so let's calculate the outlet temperature. So if we now calculate the outlet temperature based on this equation using the inlet temperature, the wall temperature, E to the minus into U's, the outlet temperature is 19.87. Okay, so again, if we make a sketch of this situation, then there's our surface temperature, which remains constant as 0. Our water inlet temperature was 20 over the length of 200 meters, and we will almost not even see the temperature change. It's going to be 19.87 degrees Celsius. Okay. Okay, so as an engineer, if this was given your job to determine if the oil is going to freeze or something like that, then you'd say, phew, at least my mistake wasn't that serious. Okay, it's still the answer is no, it's not going to change. You agree? However, there's going to be one mistake that you're going to make, and that is with a pump power. Your pump is going to be far too small. I'm going to show it to you just now. Okay, so the LMTD, again, look at that before you do the calculation. Look at it and say it should be approximately that much. Do the calculation. Okay, it is 19.87 degrees Celsius. So calculation is approximately correct. Okay. Calculate the heat transfer rate. 61.1 kilowatts. Okay. The friction factor, 64 divided by the Reynolds number, which is actually not correct because this is the value for fully developed flow. This is the value for fully developed, and your flow is not fully developed. But in your textbook, you do not have other information, so I forgive you, and you can use that equation. Okay, but it should be more than that. Okay, do you agree? Of course, it's developing. Okay, so if you go and do that, it would be equal to 0.1006. And if you go and calculate the pressure drop, then the pressure drop is going to be 119 kPa. And the pump power is going to be 168 kilowatts. Now see, unfortunately, I didn't write down the pump power for the previous case. But pumping power is going to be more because of the changes in properties. So therefore, you have to be very careful for that. Right. Do you all understand this problem? Okay, good. Now, up to now, we've done laminar flow. Now we're going to do the part on turbulent flow in 5 minutes. Okay, so turbulent flow. Turbulent flow in tubes. I'm not sure if it is chapter 8.5 or 8.6. 8.6, thanks. Okay, so paragraph 8.6. Right. Now, if the flow is turbulent, okay, then the friction factor equation is given by what is called the Petikov equation. And the friction factor equation is something like 0.790 multiplied by the ln of the Reynolds number minus 1.64 divided by minus 2, and that is equation 8.65 in your textbook. Okay? Now you have to look in your textbook. There are quite a number of equations. I'm not going to write all of them down. I'm just going to lead you through the equations. So you can see the friction factor as a function of Reynolds number. Okay? Take note, it's for turbulent flow. Then it starts with what is called the Chilton-Colburn equation. And the Chilton-Colburn equation gives the Nusselt number as equal to 0.125 multiplied by the friction factor, multiplied by the Reynolds number, multiplied by Prandtl to the third. And that is equation 8.66. Okay. Now when we started with this chapter, I hope you remember, I've said that in this chapter and in the next chapter, what is important is that the heat transfer rate is a function always of the Reynolds number, the Prandtl number, and the Grashof number. Now the Grashof number is where we've got natural convection. So there are small changes in temperature and that causes flow changes. But in turbulent flow, this falls away. In turbulent flow, the natural convection is so small in comparison with the rest that in all cases, the Nusselt number is a function of the Reynolds and the Prandtl. And you will start seeing it here. Okay. Then, the next one is called the Colburn equation. The Colburn equation is equal to Nusselt number is equal to 0.23 multiplied by Reynolds to the 0.8, Prandtl to the third, and that is equation 8.67. Okay. Now take note, in the fine print, this equation is valid for Prandtl numbers larger than 0.7, that's smaller than 160. And the Reynolds numbers should be larger than 10,000. Okay, so just after transition where the Reynolds numbers might be 3,400 up to 10,000, that equation is not valid. It's only valid for Reynolds numbers of 10,000 and more. Right, and after that follows the Dittes and Boulter equation. And the Dittes and Boulter equation is the Nusselt number is equal to 0.023, Reynolds to the 0.8, Prandtl to the n. Okay, and what is this n? N is the case where the fluid is being heated, and n is equal to 0.3 where it is being cooled. Okay. Now why all these equations? Well, these equations are the old equations as they were developed firstly, more than 60 years ago. And the accuracy of them actually sort of increased because all of them did go back to the original data and they did go and make some adjustments in the equations. However, the accuracy is plus or minus 20%. Okay. Then, after that follows the other equations, follows the Peterkov equation, and then the last one is the Gliński equation. Okay, and the Gliński equation, you'll see the equation, the Nusselt number is equal to the friction factor divided by 8, multiplied by a Reynolds minus 1,000, multiplied by a Prandtl, divided by 1 plus 12.7, multiplied by the friction divided by 8, 0.8, Prandtl to the 2/3 minus 1. That's equation 8.71. And that is sort of considered as the most accurate of all the equations. But you'll see, you'll have to put in more work to get to the equation. Okay. Okay. Now in our group, we've been working on this for the past few years, and we've got an equation with an accuracy of plus or minus 5%. And we will publish it very soon. So that would be the Meyer et al. Equation that will most probably be used in future. Okay, it's still coming. Okay, but take note, it must still be published. It must still be published. Okay. Now, the question is, if you now have a case where you've got turbulent flow through a tube, which equation must you use? Well, of course, if you're in industry and you really want to be accurate, then you use this equation, or you're going to use our new equation. But you'll see in most cases, I just use one of the simplest ones just to start with. In many cases, it is easier, it is less work. And you are fine to do that in this course, except if we tell you not to do it and we want a very accurate solution. Okay? Right, ladies and gentlemen, thank you very much. It's the end of this lecture. And I hope you enjoy the rest of your day.